Have you ever poured yourself a cold drink, dropped in a few ice cubes, and watched them bob right to the surface? It's something we see all the time, so much so that we barely even think about it. We have a very basic, intuitive understanding of how the world works. If you take a rock and drop it in water, it sinks. If you take a piece of steel and drop it in water, it sinks. Solids in our minds are dense and heavy. Liquids are fluid and flowing. We expect the solid version of a substance to be heavier than its liquid form. It just makes sense. So when water freezes into solid ice, our intuition tells us it should become denser. It should become heavier for its size. It should sink. Yet it doesn't. Every single time ice floats. This isn't just a small curiosity. It is a direct conflict with our expectations. It presents a profound puzzle that challenges our everyday assumptions about the physical world. To understand why this is so strange, we need to look at almost every other substance on Earth. From wax to iron, the rule is surprisingly consistent. When you heat a substance, its molecules get excited. They vibrate, move around faster, and spread further apart. This makes the substance expand and become less dense. When you cool a substance, the opposite happens. The molecules slow down, they lose energy, and start to huddle closer together, packing themselves into a tighter and tighter space. Think of liquid wax solidifying into a candle. If you were to drop a piece of solid wax into a vat of melted wax, it would sink straight to the bottom. Think of a blacksmith forging steel. If a chunk of solid steel could be placed into molten steel without melting, it too would sink. The solid is denser than the liquid. This is the rule. So the great mystery, the fundamental question we must confront, is why water refuses to play by these rules. Why is water the great exception? The answer isn't in what we can see with our eyes, but in the hidden world of molecules. It all begins with the unique shape and nature of a single water molecule. We all know the formula H2O, one atom of oxygen bonded to two atoms of hydrogen, but the way they are bonded is the key. The water molecule isn't a straight line. Instead, it's bent, forming a shape that looks a bit like a boomerang or a wide V. This specific shape is the first clue. Because of how the atoms share their electrons, the oxygen end of the molecule has a slight negative charge, while the hydrogen ends have a slight positive charge. This property is called polarity. It means the water molecule acts like a tiny magnet, with a positive side and a negative side. And magnets, as we know, like to stick to each other. This special attraction is called a hydrogen bond. In liquid water, these bonds are forming, breaking, and reforming trillions of times per second. This constant jumble allows the molecules in liquid water to slide past one another and pack together quite closely, but without any rigid, fixed structure. Now let's start cooling this liquid water. As the temperature drops, the molecules slow down, just like with any other substance. They start to lose energy. As they slow, they begin to pack closer together, and the water becomes denser and denser. This trend continues as we cool it from room temperature down to 10 degrees Celsius, then to 5. Everything is behaving as expected. The water is getting denser as it gets colder. But then, something truly remarkable happens right around 4 degrees Celsius. At 4 degrees Celsius, water reaches its maximum density. It is as tightly packed as it can possibly be in its liquid state. If you continue to cool the water from 4 degrees down to 0, the trend suddenly reverses. Instead of becoming denser, the water starts to become less dense. It starts to expand. This is completely counterintuitive. Cooling it further makes it expand. This is where water's special nature truly reveals itself. Instead, they begin to lock into place. The molecules don't just clump together randomly. They start to arrange themselves in a very specific, orderly pattern. When water finally freezes at 0 degrees Celsius, the molecules are no longer free to move. They are locked into a beautiful six-sided structure known as a crystalline lattice. Think of it like a group of people dancing in a crowded room. When the music is fast, everyone is jumbled together closely. That's liquid water. But when the music slows down and they begin a formal, choreographed dance, they have to stand at arm's length from their partners in a set formation. They take up more space. This is exactly what water molecules do. The hydrogen bonds lock them into a hexagonal pattern, creating a crystal structure with a surprising amount of empty space in the middle. This empty space is the secret. Because of this fixed open lattice, the molecules in solid ice are held further apart than they were in the densely packed liquid water. Fewer molecules in the same amount of volume means lower density. This is it. This is the reason ice is less dense than water. This expansion is why a can of soda left in the freezer will explode. The water inside expands as it freezes, pushing against the walls of the can until it bursts. So the puzzle is solved. The unique V-shape of the water molecule and the behavior of its hydrogen bonds force it into an open, expanded crystal structure when it freezes. This structure takes up about 9% more space than the liquid water it came from, and because it's less dense, it floats. For almost any other substance, the solid sinks in its own liquid. But for water, the solid floats. We've now escalated from a simple observation to a deep molecular truth. We have uncovered the hidden mechanics behind a seemingly simple phenomenon. But the story doesn't end here. The why is fascinating, but the so what is breathtaking. This single, strange property of water is not just a scientific curiosity. It is one of the most critical factors for the existence of life on our planet. Imagine a world where water behaved normally. Imagine a world where ice was denser than water and sank. In the winter, as the air got cold, the surface of a lake would freeze. But that ice would immediately sink to the bottom. Layer by layer, the lake would freeze solid from the bottom up. The same would happen to rivers, and eventually, even our oceans. This would be catastrophic. All the fish, plants, and other organisms living in the water would be trapped and frozen. Aquatic ecosystems as we know them could not survive the winter. But that's not the world we live in. We live in a world where water breaks the rules. The floating nature of ice is not a flaw or a mistake. It is an incredibly elegant and essential feature of our planet's operating system. Because ice floats, it forms a protective layer on the surface of a lake or an ocean. This layer of ice acts as an insulator, shielding the liquid water below from the freezing cold air above. Underneath this floating blanket of ice, the water remains liquid. It stays at a stable temperature, allowing fish and all other forms of aquatic life to survive the harsh winter. This one weird trick of chemistry, that ice floats, is nature's solution to protecting life in cold environments. It creates a stable habitat where life can thrive, even when the world above is frozen. So the next time you drop an ice cube into your glass and watch it float, you're not just witnessing a simple physical act. You are seeing a demonstration of a profound natural law. You are watching the very property that keeps our planet's lakes and oceans from turning into solid blocks of ice. You are observing the principle that has allowed life to flourish in water for billions of years. The fact that ice floats is not just a piece of trivia. It's a reminder that sometimes the most important rules are the ones that are broken.